Okay, so that is everything that I want to say about limits which go to infinity. But I'm not done talking about limits and infinity. There's a little bit more I can do. All of my limits so far have been about x approaching a particular coordinate. I've been calling it a. Sometimes my a is 0. Sometimes my a is 1. It hasn't happened yet that my a has been negative pi, but I guess it could happen. Any real number. I can also talk about limits in which x itself tends towards infinity. So I get 2 for 1 on my graph today. Here it is again. This is the graph in red of the function y equals 1 divided by x squared. Forget about that, infinite limit there. We'll put that away for right now. But now notice, as I go out further to the right, I'm taking larger and larger values of x. I'm dividing by a larger and larger number. And this graph seems to be flattening out. So the same way that I talk about limits when x approaches some a, I can have a similar idea for limits in which x approaches positive infinity or in which x approaches negative infinity. Right? So this is kind of a jump up in the conceptual thinking. The idea, this limit exists, I'm going to call it capital L. And here my capital L is a real number. So 0 on the graph I was looking at. The limit's going to be 0. This relation is going to be true. The limit of f of x as x tends to infinity equals the real number L if x can be made to stay as close to L as we like by taking x to be ever larger positive values. So note that this limit is x going to positive infinity. And I can also go the other direction. I can talk about limits in which x goes to negative infinity. My f of x can be made to stay close to as I want to the real value L by taking x to be negative numbers of ever larger magnitude. So going ever larger in the negative x direction. Now, if either of these exist, and we get a finite number L, then y equals L is going to be a horizontal line, and I will call that the horizontal asymptote of the function. So here's my graph. As x tends to positive infinity, my function, my y coordinate, is tending towards 0. So I'm going to graph in the line y equals 0. There it is in green. It kind of just overlaps with the x-axis. This is going to be my horizontal asymptote, the same way as my blue line, x equals 0, was my vertical asymptote. So it's a line which the graph of the function is getting closer towards. So this is just like we had for the previous video, but now horizontal instead of vertical. And that's pretty much it. Now, we'll usually only talk about these limits as x goes to infinity when that's going to be a number. Technically, you could talk about this limit also being infinity, right? We could see that in a function, say, y equals x. That's one of the easiest functions there is. If I go to positive infinity on the x-axis, my y variable is also going to positive infinity. That limit does not exist, right? That shouldn't be too surprising at this point. I could say that that limit equals infinity, but it's also not as helpful, right? It's a fascinating thing when I have 1 divided by the square root of x cubed. I think it is. And as I go out further to the right, I'm getting smaller and smaller values of y, and this will be tending to 0 as x goes to infinity. I think that is wonderful and amazing. And it actually has some very interesting properties for the kinds of calculus that we will be doing when we talk about rates of change and accumulation. It's a bit more interesting than just saying, well, the function y equals x goes off to infinity as x goes to infinity. That's basically a tautology. I'm not sure I said anything interesting there. But now we have new language for talking about these special kinds of limits.